Hello guys, welcome back to our channel. So today we're going to learn about the second law of thermodynamics. So actually there are many definitions of the second law of thermodynamics. So the famous one is a spontaneous of closed system generates entropy and involve heat moving from a hotter body to a colder body. So based on this definition, we can get the three key points that you must understand it properly. The first one, the spontaneous. So what is the spontaneous? Actually, the spontaneous is the process that does not drive by outside heat. The process that does not drive by the outside force. Next, the closed system. The closed system means the system does not allow any movement of the mass and energy. So lastly, the entropy. What is the meaning of entropy? So usually entropy is represented by a small capital of S, and the famous definition of the entropy is the measure of the disorder of a system, or we can also define it a direct measure of each energy configuration probability. So next I will give us one example to make you understand about it. Look here, I have a cup of milk and I also have a cup of coffee. So in the molecule we can see the state of the molecule of milk in organized, and also the coffee, the molecule in organized. So then when I mix milk and coffee, we can see it. The molecule is in disorder state. So we'll go to the second example to make you more understand. So I have a cup of coffee 70 degree and a cup of coffee 10 degree. So you can imagine I want the first cup to be more hotter above the 70 degree. So is it possible that I take a heat from the second cup, move to the first cup? Yes, it's make no sense, because heat only move from the high quality to low quality, or move from the hotter body to a colder body. This is entropy, and is the system is a high entropy because it tends to spread out its energy, and the system is a low entropy because it tends to concentrate of energy. So based on this explanation, I hope you guys understood about the definition of the second law of thermodynamics and definition of entropy.
We learned that heat engines are machines or systems that convert heat into other forms of energy. Based on the concept of second law of thermodynamics, it is impossible to extract an amount of heat from a hot reservoir and use it all to do work. Some amount of heat must be exhausted to a cool reservoir. This is sometimes called the first form of second law, and is referred to the Kelvin-Planck statement of the law.
Another vital application of second law of thermodynamics is found in refrigerators and heat pumps, which are based totally at the precept of reverse Carnot cycle or reverse Carnot theorem. The second law of thermodynamics says that warmness can warp from excessive temperature reservoir to low temperature reservoir simplest, but in case you need to transport the warmth from low temperature to excessive temperature reservoir, then the external work has been supplied. The authentic Carnot cycle corresponds to the heat engines in which work is produced. In this cycle, heat is absorbed from the excessive temperature reservoir and released to the low temperature reservoir, and the work is produced. In the reverse Carnot cycle, the works are provided to the cycle, and the warmth is transferred from low temperature reservoir to the high temperature reservoir. This is what precisely the second regulation of thermodynamics say. Our refrigerator, the freezer is maintained at low temperature through casting off the heat from it and throwing it to the environment, which is at better temperature. This does now not happen automatically. We should supply energy that is used to run the compressor of the refrigerator.
The network output of this power plant is the difference between the total work output of the plant and the total work input. The network can also be determined from the heat transfer. From this figure, it can be analyzed as a closed system. No mass can enter or leave this combination system. For a closed system undergoing a cycle, the change in internal energy is equal to 0. Therefore, the network output of system is equal to net heat transfer to the system, which is W net out is equal to Q in minus Q out. Based on equation W net out equal to Q in minus Q out, Q out represents the magnitude of the energy wasted in order to complete the cycle. The value of Q out are not equal to 0. Thus, the network output of a heat engine is always less than the amount of heat input. So, only part of the heat transferred to the heat engine is converted to work. The fraction of the heat input that is converted to network output is a measure of the performance of a heat engine, which is called the thermal efficiency. For the heat engines, the desired output is the network output, and the required input is the amount of heat supplied to the working fluid. Then, the thermal efficiency of heat engine can be expressed as thermal efficiency equal to network output divided by total heat input, or thermal efficiency is equal to W net out divided by Q in. It also can be expressed as thermal efficiency equal to 1 minus Q out divided by Q in. Cyclic devices of practical interest such as heat engines, refrigerators, and heat pumps operate a high temperature medium at TH and low temperature medium at TL. To bring uniformity to the treatment of these devices, we define those two quantities as QH and QL. QH can be defined as the magnitude of heat transfer between the cyclic device and the high temperature medium at TH. QL also can be defined as the magnitude of heat transfer between the cyclic device and the low temperature medium at TL. These quantities are positive quantities. The direction of QH and QL is determined by inspection. Then, the network output and the thermal efficiency relations for any heat engine can also be expressed as W net out equal to QH minus QL, and the thermal efficiency is equal to W net out divided by QH, or 1 minus QL over QH. The thermal efficiency of heat engine is always less than unity, since both QL and QH are defined as positive quantities.